Hello, this is Rowdy Chemist Jr. bringing you another exciting video in general chemistry. Most of my videos involve full-length lectures where I go through lots of topics in a particular chapter or particular subject. But here I'm trying something new called Quick Bits. So in Quick Bits, I pick one particular topic and kind of cover that topic either through doing an example problem or discussing it conceptually. And the first Quick Bit uh, video I'm doing is on the heats of formation. So sit back, relax, and enjoy the show. And so here I typically like to use fictional or made up elements, compounds, or problems. And so in this problem, I've taken aspects of from the movie Lord of the Rings and kind of incorporated it into my problem. By no means do these statements or this information have any relevance to the actual Lord of the Rings movie. So here in Middle Earth, there's a mystical element called mithril, which exists as the compound Mi3H4. Frodo frequently uses this compound to produce heat to cook his food. Calculate the heat of formation of Mi3H4 given the following information. So what we're looking for here is the heat of formation of Mi3H4, and we're giving the balanced chemical equation and the delta H of reaction. Additionally, we're given the heats of formation of H2O gas and MiO3 gas. This is a gas here. So the heat of formation of O2 is not given because the heat of formation of O2 equals 0 because O2 is the natural state of oxygen. And so O2 is 0 because O2 is oxygen's natural state. It's going to have a heat of formation of 0. So anything in its natural state has a heat of formation of 0. So now remember the delta H of reaction involving heats of formation equals the delta H of reaction equals the sum of the heats of formation of products minus the sum of the heats of formation of reactants. Now remember, this also has to be multiplied by the coefficients in front of the reactants and products. Let me draw the sum sign here. So when we work this out based on our reactants and products, we get the delta H of reaction equals, and so here there's a 6 in front of MiO3, so it'll be 6 times the heat of formation of MiO3 plus 4 times the heat of formation of H2O. So again, the coefficients are important because we multiply the heats of formation by it. And then we're going to subtract it from the heats of formation of reactants. So here for reactants, we have 2 times the heat of formation of Mi3H4 plus 11 times the heat of formation of O2. Now, since the heat of formation of O2 is 0, we can go ahead and disregard this. So this will just be 0 right here. And so again, what we're looking for is the heat of formation of Mi3H4. So if we rearrange this equation, we get 2 times the heat of formation of Mi3H4 equals the heat of formation of products then we're going to subtract it from the delta H of reaction. We'll deal with the 2 in just a moment. So now we have all this information. We have the information of the heat of formation of MiO3, the heat of formation of H2O, and the delta H of reaction. So now we can plug these in and solve for our unknown. Six times so that's the heat of formations of products multiplied by their coefficient. Now, since delta H is negative and we're subtracting, that's going to be a positive 4,250. So now, if we simplify this, we get negative 2,920.88 plus 4,250. So now we can solve for 2 times the heat of formation of MiO3. And we get a positive 1329 kilojoules of heat. Now we need it we need the heat of formation of Mi3H4. So now we got to get rid of this 2. So this would be heat of formation of MiO3 is equal to 1329 divided by 2. And we get a heat of formation of 664 kilojoules per mole. So this would be the heat of formation of Mi3H4 for this reaction. So again, my apologies for the typo. This should be Mi3H4. Let me put that correction here. So now if you wanted to check your work, what you can do is you can put this heater formation in and solve for the delta H of reaction to see if we do indeed get negative 4,250. So to check, delta H of reaction equals 6 times the heat of formation of MiO3 plus 4 times the heat of formation of H2O gas and all of that subtract 2 times the heat of formation of Mi3H4. And so we get a delta H of reaction. And, because of rounding, it may not be exact, but it'll be very close. And so when we work this out, we get a heat of delta H of reaction of negative 4,248.8. But if we round this to 3 significant figures, we get negative 4,250 kilojoules per mole. So our heat of formation of Mi3H4 is correct. So again, this was just a quick bit on how to go about solving uh, problems that involve looking for or calculating the heat of formation of a reactant or product when given the delta H of a reaction. So I hope this video was beneficial. If you'd like to, click the like button in the chat so I know to make more videos like this. Until next time, Browdy Chemist Jr. signing off.